Hi, pre-calc students. This is going to be our last day of the functions unit. Today we're going to talk about inverse functions, and this is on page 23 and 24 in your packet. So this is going to be fairly a review of what you would have learned in Algebra 2 last year about, first of all, how to find an inverse function, and then some other relationships that exist among inverses graphically, algebraically. You're going to see we're going to fill in this chart about domain and range here. So to get started, why don't we look at the function f of x and get started by just plotting it right away. So we have 3x minus 3 as our function. That's a linear function with a y-intercept of -3. And with our slope of 3 over 1, we can rise 3 and run 1 and find a few other points on the line, however many you need to ensure some accuracy here. Okay, and there's my function f of x. So once you have that plotted, now we can talk about how we're going to find the inverse of this function. And what you might remember from last year is that the whole idea behind inverse is that we switch x and y. Okay, so when we switch x and y in this example, f of x we know is the same thing as y equals. So if I switch x and y, we get x equals 3y minus 3. And it's not only about switching x and y, it's once you've switched them, now we have to solve for y again. So to get y alone, we're going to add 3 to the other side. So x plus 3 is equal to 3y. And finally, dividing both sides by 3 gets you the equation y equals x plus 3 over 3. If you didn't remember this, maybe the chart here is helping you to remember that the notation for inverse is f to the -1 of x. So that's going to be x plus 3 over 3. If you wanted to, you can divide both items on top by 3. Okay, both terms on the top. This way we get something that's a little bit easier for us to sketch. I think this is more recognizable that the inverse is also a linear function that has a y-intercept of +1 and a slope of 1/3. Okay, so if you start at 1 and rise 1, run 3, and use that pattern for a little while, you can get a nice accurate sketch for the inverse, which we can label on the same set of axes. And now that we've done that, we can go ahead and start filling in some of the table information here. So for the original function f of x, it's pretty easy if it's linear that we can conclude that the domain and range are all reals for both of those. Okay, so we've got -infinity to infinity for both. And since the inverse was also represented by a linear function, we can say the domain and range for the inverse is also -infinity to infinity. We've got all reals there as well. But before we move on to the next example, there's definitely some things that I want you to start thinking about the relationship between the graphs of these two functions. So that's one of the conclusions we'll make by the end of today. Is there a relationship graphically? Well, there definitely is. But what is that relationship? Hopefully through a few more examples, you'll start remembering what that is. And then what I want to know is the inverse a function? And if we look at the graph of the inverse, yeah, linear functions, okay, are definitely still passing the vertical line test there. So we can say yes, that the inverse is a function, and the conclusion we'll make is if we say yes to that question, that means that the original function f of x is what we call 1-to-1. So one thing that we'll add on to our just vocabulary quickly with inverse functions is if the inverse also is represented by a function, then we know that the original function f of x is 1-to-1. There's a 1-to-1 correspondence between x and y values. All right, moving on to the next example, we've got f of x equals x squared. Boy, we've graphed that a lot, haven't we, right? I mean, this is apparent. We should be really good at by now by starting at the origin. You can go maybe get a few other points, right? The outputs at -1 and +1 are both 1. And then if you plug in 2 and -2, we get those y values of 4. So there's my original function f of x. And while I have the red pen in my hand, I might as well come to the table and quickly talk about domain and range here. Domain of the function x squared is all reals, goes to the left and right forever. But meanwhile, the range, if I go from bottom to top, we know that the lowest y value is 0. And it's 0 with a bracket to infinity. All right, so let's talk about then how do we find the inverse equation. So in this example, we're going to write, if we have y equals x squared, we've got to switch x and y. Okay, so when you switch x and y, in this case, you get x equals y squared. And then it's a pretty quick algebraic step to get y alone, right? We're going to take the square root of both sides. But one thing you do have to be cautious about is that when you are solving something and you take the square root of both sides, you really have to consider that it's plus or minus the square root of x. So that winds up representing our inverse equation here. It's plus or minus the square root of x. And we know what radical x looks like. So if we have radical x, that also has 0, 0, and 1, 1 on it. If you plug in 4 for x, the output there would be 2 for the inverse. Okay, so that part's just the radical x. But we also have to graph negative radical x with this. And what that does is it takes the graph that we just sketched up above and flips it over the x-axis, according to what we know about function transformations. So when I graph the inverse, f to the negative 1 of x, we get this resulting graph right here. So if we fill in the domain and range, let's see, domain from left to right for the inverse. Domain would go this time from 0 all the way to infinity. And although it's very slow growth with these radical functions, this graph will head up forever. And this graph on the other side will head down forever. So the range, maybe not as obvious, but it is all reals there, negative infinity to infinity. All right, so that's a little weird, but comparing what we had in the first example to what we have now, maybe you're starting to see that graphical representation relationship between f of x and then the inverse. But I'm also hoping it's very clear that f inverse in this example is not a function. This definitely fails the vertical line test. So the conclusion is if the inverse is not a function, that means that f of x is not 1-to-1. Okay, so that's going to be something we definitely want to think about in terms of making some conclusions later on. Okay, so the inverse is not a function, which means f of x is not considered to be 1-to-1 in this case. What I might ask you later on is, looking at the original function f of x, how would I have known that in advance? How could I tell, looking at f of x, that it's not 1-to-1? That might be something you remember from last year too. All right, I think we've got one more to do. That's it. So if we look at the square root of x minus 2, I'm going to get my red pen again. We just graphed a radical x function a second ago, so we should be really good here that radical x minus 2 shifts that graph to the right 2 units. So we're going to have a starting point at 2, 0. You plug in 3, you get 1. Plug in 6, you get 2. Those are just some quick key points that we can sketch there for the original function f of x. So when I go to find the inverse here, maybe I'll do domain and range quick while I'm at it. Domain is 2 to infinity. Range in this case would be 0 to infinity. We fill those in. When we go to do the inverse, we're going to switch x and y. So we get x equals square root y minus 2. And then we're going to go ahead and get rid of the radical, in this case by squaring both sides. So opposite of what we did in the last case, right? In the last example, we had an x squared, so we square rooted both sides. In this case, if you have a radical, to get rid of the radical, the inverse operation is squaring both sides. So we get x squared equals y minus 2. So a really quick step of adding 2 to the other side gives you the equation x squared plus 2. And therefore the inverse, f to the negative 1 of x, is x squared plus 2. Okay, but there is an exception to this rule here. Okay, so the inverse is in fact x squared plus 2, but there's going to be a little bit of an issue there. Okay, so let's go back to the last example that we just looked at, and I want you to now start thinking about what is this relationship graphically between a function and its inverse. And what I'm hopefully thinking about here is that there is some sort of reflection happening here between these two graphs. And that reflection that we see is it gets reflected over the line y equals x. So maybe that sounds familiar. And in fact, when you switch x and y in the coordinate plane, that's the type of reflection that happens. Maybe you remember that from the good old geometry days. Okay. Same thing up here in number 1. If you draw the line y equals x in it, it should look like a mirror image over that line. So if we go back to the example we were just working on here, if I think about taking this graph and flipping it over the line y equals x, I don't think I'm going to see exactly what I would expect to with x squared plus 2. I mean, x squared plus 2, isn't that a full-on U-shaped parabola there? In fact, why don't I just take the points that I have right here, switch the x and y values, and plot those? That's a quick way to graph an inverse as well. So 2, 0 would match up with 0, 2. 3, 1 would match up with 1, 3. And then 6, 2 is going to match up with 2, 6. Okay, so there's what the graph of the inverse is going to look like if I label that real quick. So I'm not seeing the full-on parabola. I mean, x squared plus 2, isn't that a parabola that got shifted up? Like, where's this side right now? You know, this side, this dotted part, you're definitely not seeing that when you graph the inverse. The inverse is only this side of the parabola. So when I write down the inverse equation, I do have to be a little cautious here and say I'm seeing x squared plus 2, but only for x values that are greater than or equal to 0. I'm not seeing it for any negative x values. So why does that happen, that we're only seeing it for x values greater than or equal to 0? Well, it happens to do something with domain and range of a function and domain and range of the inverse. It's probably not as easy to recognize in the first example because all those domains and ranges were all reals. But look what happened in the second example. Domain was all reals. Oh, wait, that's the range of the inverse. Here the range is 0 to infinity. Notice how that became the domain of the inverse. So there's definitely a special relationship happening there with domain and range. So the inverse should have a domain of 0 to infinity. And the range here is 2 to infinity. And we can confirm that by looking at the graph. Yeah, the domain is 0 to infinity. The range is starting at 2 up to infinity from there. So the thing that's weird about this is that this function doesn't naturally have this domain. X squared plus 2 typically has a domain of all reals. But when it represents the inverse of this original function f of x, which is a radical function, because the radical function has a restriction on the range, it winds up restricting the domain for my inverse equation. So this doesn't happen too often. I mean, when will it happen? Typically with radical functions is what we'll see. So I would like you to think about that when you find the inverse, putting that qualification on it, that x has to be greater than or equal to 0. You're not seeing this whole function graph, you're only seeing the right side of it. That definitely takes some time to get used to. All right, is the function f of x 1-to-1? So it either is or isn't. Let's see, does the new function, the inverse, pass the vertical line test? The answer is yes, the inverse is a function. So f of x is in fact 1-to-1. Remember, when I'm looking at the inverse, I'm not looking at this side of it at all. Okay, I was really just considering this part. But either way around it still passes the vertical line test. So f of x is in fact 1-to-1 because the inverse is a function. All right, so let's make some quick conclusions then. And this is just something that I already actually have pre-written, so you'll have to copy down into your packet on page 24 here. Here are some conclusions I want you to come up with. Number 1, the graphical representation of a function and its inverse is the relationship is we get that reflection over the line y equals x. That's pretty well established at this point. We drew it in each of the examples, so hopefully that makes sense. And again, the nice thing that I used here is that if you switch the x and y values, you get that graph of the inverse immediately. And that might help you to start thinking about, like, are there any restrictions on my inverse equation? You know, this is a unique case, but something that is important to include. All right, number 2, the relationship between domain and range, also something I've already mentioned in the video here. The domain of the function becomes the range of the inverse, and then vice versa. The range of the function is the same as the domain of the inverse. Definitely an important relationship there. And then finally, we talked a little bit about 1-to-1 for all these examples. So a function is 1-to-1 if the original function f of x passes the VLT and HLT. So we didn't really talk about that. But if you're looking at the original graph for f of x, so this red graph right here, if it passes the vertical line test, it's a function, which all of them are functions to start. But if it also passes the horizontal line test, meaning you can draw a horizontal line and it only hits once, that means it's a one-to-one function. So if you look back at number 2, this was not one-to-one, but notice how it fails the horizontal line test. Horizontal line would hit more than once. Okay, so a couple quick conclusions there. And again, what this means is if the function is in fact one-to-one, that means that the inverse is a function. Okay, so some good solid conclusions based on what we know about function inverses. There's a little bit more that we'll recap next time when we talk about inverses in class. Here's kind of a last one that hopefully you have some space at the bottom of your page to give a shot. This one's actually pretty tricky, so challenge yourself. See if you can do it. Hopefully I haven't scared you away by saying that that's a little tougher. Okay, but if you can do this one, you can probably do any other inverse algebraically. But we'll go over this one first thing tomorrow. We'll talk a little bit more about function inverse properties. And if you have any questions, let me know. Have a good day.